Tina Eliassi-Rad, I am not going to do you justice. You have a lot of awards. But what I will say about Tina is that she does not flinch from the hard questions. And I really appreciate that and honor that. She sets the ground the rest of the day stands on. Tina is the inaugural Joseph Yuan, if I'm saying that right, professor at Northeastern University. She has been working for decades at the intersection of AI and network science. She's advancing our understanding of the impact of science and technology on society. She was named one of the 100 brilliant women in AI ethics in 2021. She has received numerous awards. This is the super short bio that she gave me, so you can imagine what else is in the longer bio. She was elected Fellow of the Network Science Society in 2023, and there are many, many more awards. I do not want to make her uncomfortable. So please join me in welcoming Professor Tina Eliassi-Rad, our first morning keynote speaker.
Thank you so much. That was very, very kind. I'm so happy to be here among you guys today. So let's talk about our human AI society. In 2021, we wrote a paper talking about how we live in algorithmically infused societies, where basically our algorithms and our human behavior are woven together. And what we need to do is understand what is happening. And just as an example, there was a recent study at Stanford that said over 50% of people are meeting on online dating apps. And now with generative AI, it's even on hyperdrive. We don't understand what these algorithms are actually doing. And so that makes you pause, for example, right? There's obviously Amazon with the recommendation systems, a lot of these kinds of e-commerce, where you give it your data, the data goes into the algorithms make recommendations, those recommendations affect you, and round you go. This affects science, politics, etc. Or we're at a higher ed education system. The AI tutor business is over $500 million. With over 200 plus institutions that are part of it and over 1 million students. Do we know exactly how students use these AI tutors? Do we know the inside of these AI tutors? We as professors know about pedagogy. And so we should look into this and see how students are using it, these AI tutors, and be able to help them in terms of their learning. Going back to the paper, we listed 3 challenges. One was insufficient quality of measurements. The other one was the complex consequences of mismeasurements. And the third was the limits of existing social theories. And I just want to highlight the complex consequences of mismeasurements. Oftentimes, people don't think about what should be measured and what should not be measured. In a seminal paper in Science in 2019, Zaid Obermeyer et al. Wrote about an algorithm that is being used in many systems that are in healthcare, used across the country, where you really want to predict the severity of illness, but because that's a hard prediction task, you replace it by a seemingly innocuous proxy predicting healthcare costs. Well, that is not a good proxy to use if you care about predicting severity of illness. Why? Because in America, we do not spend at the same rate among our various subpopulations. And so the subpopulations who are on the lower socioeconomic status get harmed by this algorithm. And who is responsible for it? Who can you sue, right? We live in America, it's a very litigious community. Nobody, right? So we are at an age of turbulence with this AI, and it's affecting our lives. And we need to come to an equilibrium where when harm happens, somebody is responsible for it. So more recently, we had a paper in the AI journal talking about human-AI co-evolution. So when we wrote our first paper, that was before generative AI, and now generative AI is here. And so we spilled out this notion of we are, in fact, co-evolving with the generative AI systems. The process is similar to the feedback, right, where you as users produce training data for the companies, they use it, they give you suggestions, you take the suggestions, you give them more training data, and round and round you go. And just to bring this home, this past summer, my husband and I were in Athens, Greece, and we took a picture at the Acropolis. So the reality is Acropolis is a popular tourist destination. But on my iPhone Photos app, there is a cleanup feature. Obviously, I don't want the people in there. So just on my iPhone, I can get rid of the people. Now, this is obviously the thing I'm going to upload. This image, the enhanced image, is obviously what I'm going to upload to social media, et cetera, et cetera. I bet you guys would do it too, right, the enhanced versions. But then the AI systems will learn that Acropolis is not a popular tourist destination, and I couldn't get rid of the crane. Maybe it will learn that it's just a construction site. And then what happens is, with these AI assistants, they're not completely accurate. So if you pay attention, you will see shadows of people without people. And if you pay even closer attention, you will see just the calf by itself. No other parts of a human being, right? And so they are not really learning what the physical world is about. They're learning what we are giving them, and we use AI to give them an enhanced version of our world. And so in that paper, we highlighted both scientific challenges, legal challenges, and social political challenges. The one thing in terms of scientific challenges, since we have so many smart students here, is to actually find this bidirectional causal feedback loop of how much is the AI assistant affecting you and how much are you affecting it, right? And how does this scale up? We need new scientific frameworks to study this. The old scientific frameworks, your fathers, your mothers, your grandparents' scientific framework do not fit here. So if you think about Judea-Pearl's scientific causal models, no. If you think about Rubin's potential outcome models, no. You have to come up with your own. Then, of course, we need legal, there are legal challenges. We need new laws where, for example, how can we have a legal transparency framework? And also, how can we distribute all this goodness across our population and not just to the very top? And so this brings us to the AI is really generative AI nowadays. And this picture is from Rapid Ops. It's from 2023, so it's a little outdated. But it gives you a good sense of what is generative AI being used for, right? So there is LLMs with text, there's video, there's image, etc. There's code, so on and so forth. And in this talk, I'm going to focus more on LLMs. And if you're going to take one thing away from my talk, let it be this picture. This picture is by my friend, Henry Farrell at Johns Hopkins University. The monster goes on the web, collects all the data, does not care about copyright, by and large, and all it does is it predicts what's the next word, sequence, or token. There's lots and lots of data. It can use it. It does not need human supervision to predict that when I see very, it's likely that I will see well after it. Then we put a human face on the monster when we want to fine-tune it for a specific task. For example, when I want to fine-tune it to be a lawyer assistant, like Harvey.ai. And then finally, we put a happy face on it for the safety stuff, for the alignment stuff, right, for the responsible AI stuff. Now, of course, the small happy face that we put on there is not sufficient to guarantee safety or guarantee alignment. And so 2 years ago, on the occasion of the International Women's Day, I and a group of international scholars, we wrote a report for UNESCO highlighting the misogyny and sexism in these LLMs. And I'm not going to bore you with a depressing story, but what I'm going to say is that these LLMs are trained on Western data. These LLMs are not trained on data from countries where we believe they treat their women poorly. And so the misogynistic and the sexist calls are coming from inside the house. And however many alignments, however many reinforcement learning with human feedback you put on it, you can get this sexist and misogynist responses from these LLMs, which are then going into that feedback loop. Now, you may say, wait, well, I don't have to get data from the web. I could get data from elsewhere. And this is one thing that we did. So if in the United States we live in surveillance capitalism, in Denmark they live in surveillance socialism. And so there is this Danish National Registry from which we got data for 6 million Danes from 2008 to 2020. We had labor data, we had health data, we had socioeconomic status data, lots of data. And so what we did was that everybody has a life story. Now that I have this data, can I predict what happens in a person's life? And the picture I'm showing is Karen Blixen. She was the author of Out of Africa. And so what we did was we used the transformer models, which are the heart of these large language models, to be able to map human stories into this encoding or embedding space. Basically, it's a vector space. And then based on that, we were able to do some predictions. And this work went viral in part because we had a task early mortality prediction. The idea was that if you were between 35 and 65, as of December 31st, 2015, and you had at least lived 1 year in Denmark, can we predict whether you were going to pass away in the next 4 years? And the model does extremely well. And we did a lot of auditing of the model. So for example, being male is a risk factor. And we all understand this, right? Because usually males believe that, oh yeah, I can jump over this ravine, versus a female is like, well, maybe not, right? Being a mechanic or an electrician is a risk than, for example, being a manager in an office, right? But this caught a lot of insurance companies in America are like, oh, if I could predict if somebody will die in the next few years, that would be fantastic. You cannot repeat this study in America, right? We do not have surveillance socialism. Every place has its own healthcare system. Healthcare data is notoriously noisy. What actually was very helpful here was socioeconomic status data and labor data, right? And so one has to be careful in terms of the hype and saying, oh, I saw this, I'm going to take it, and I'm going to apply it for whatever task I had. And this was so bad that there were fake Twitter sites and fake websites saying, oh, input your data and we'll tell you whether you're going to die in the next 4 years, right? Which was just nutty. It was like, oh my gosh. So then I'm going to move on to knowledge. So epistemology is about the study of knowledge. What do you know? How do you know it? How sure are you about what you know? And now, in our human generative AI society, there's so much noise and so little signal. We do not live in the era where Walter Cronkite was the most trusted man in America, right? When my father was getting his PhD at The Ohio State University, he's an electrical engineer, he would come home just to watch Walter Cronkite. There is no Walter Cronkite. You have to make sense of what is out there and separate the noise from the signal. And perhaps you talk to your friends and your community to try to hash out the noise from the signal. So some of the important questions to ask here are, what do you know? What do your interlocutors know? And your interlocutors are not just people now. They are these chatbots. And how do these interactions change what is known in society? How do we go from a society that believes vaccines are good for public health to a society which believes vaccines are not good? And we shouldn't do that. We don't care about public health, at least in that way. And so I have this research project that looks at epistemology in generative AI, where we look at veracity, stability, relevance, and feedback. And I'll quickly run through them. And then I will finish with how AI researchers deal with responsible AI and ethics. So this is work with my postdoc, German Sevchishins. What does an LLM know? It's a good question to ask. What happens is that we quote-unquote probe the LLMs to figure out what they know. At the end of my talk, I will have a QR code that you can click on and download all the slides. I forgot to mention it up front, sorry. And so one way to probing what a large language model knows is to give it a prompt, right? This is called zero-shot prompting, or you may have heard of it in terms of in-context learning. Now, it's very well documented that these zero-shot prompts are very sensitive to the prompt itself. So for example, the prompt you see here is a multiple choice question. It's a multiple choice prompt. And if I were to shuffle the choices, then the answer would be different. Now, you would say, I also see this in humans, in students, right? Because students oftentimes think the answer is B or C. So I can like shuffle the options, and I will also see this difference in the students. It's just that we see this more. We see this observation more in LLMs. And if I remove correct and incorrect in this prompt with true and false, the answer of the LLM also changes. So one of the things that the big tech companies are doing are saying that if you give us more of your data, then we can personalize it, and we can learn how, for example, Tina asks questions, and because of that, then we won't be so sensitive to the prompt. But then now you're giving even more of your privacy up, right? And we can talk about privacy during Q&A. The other thing is to actually look inside the AI assistant by looking at these models that are open weight. So there's a company called Hugging Face that if there are people who are willing to give their parameters, the learned weights of their LLMs, you can actually look through inside this box of these large language models. So famously, Meta, right, the parent company of Facebook, released all of its models on Hugging Face. And so that is what we do. So how would you do this, actually? Like, actually crack open the box and figure out what is going on. So one way is, as I mentioned, is probing, where you get some auxiliary data, like data about medical conditions and drugs, and you send the statement to a large language model, and the large language model gives you vectors. It's all a vector space. It's all what you learn in linear algebra, which if your degree is in STEM, you must have taken linear algebra, right? And now, because it's auxiliary, you know, for example, aspirin is good for headache. And so you have this label, you have a human label. So then what you do is, like anything in machine learning, or what we as professors do, you separate the training from the testing material, you learn some parameters, and then you make a boundary of anything on this side is true and anything on this side is false. So I'm showcasing this work because this work was one of the works that said geometry of truth. So what we found, that there's actually a geometry of truth behind the quote-unquote brain of these AI assistants. But what we found was there were lots of flaws in what was out there. For example, people assume that LLMs know exactly what we know. Well, that is not true, right? There are certain things you know that perhaps the LLM doesn't know. Or that there's really bi-directional, like truth this way and falsehood that way. That is also not true. What if I give you, this statement is false? Is it true? Is it false? Which way would it go? They also assume that these probabilities are calibrated. If you're a machine learning, AI, statistics, data science person, you care about calibrated probabilities because then you accurately estimate the phenomena that you're interested in. Then they assume, these are all the flaws, and the reason I'm spending time on this is that a lot of the models out there have flawed assumptions, and you need to think about what are those flawed assumptions before you use them. So one of them was that whenever you give it a statement, you know exactly where the signal for truth or falsehood is. What is the truth or falsehood of a punctuation mark? And then lastly, that you know exactly where this truth or falsehood is in a particular statement. And so I'm an AI person, I'm a machine learning person. We propose a new method to solve these issues, right? And so the new method is, we call it Sawmill. And what we do now is instead of sending one vector, we actually send the bag. So now you're giving it more context. And also we add a neither label to what the statements are. The reason for neither labels is, what would you say to the present king of France is bald? This is a statement from Bertrand Russell, who won the Nobel Prize, from his famous paper in 1905. Some things are neither true nor false. You need to have that option. The rest is similar. You break it in training and testing, you learn a classifier, you learn a machine learning model, and so on and so forth. Now, I want to emphasize this nonconformity scores because people are bad with probabilities. When somebody says the probability of it raining today is like 90%, people interpret it differently. And so having these kinds of nonconformity scores helps because it tells you, for example, how far away you are from what your learner actually learned. So by doing this, you can actually look inside an LLM and see what it classifies as true, false, and neither. So you can make these kinds of triangle plots where anything that is in the red shaded area, any statement that falls in the red shaded area, the model believes 95% that it is false. Anything that falls in the blue shaded area, the model believes that it's 90% true, and anything in the green shaded area, the model believes that it's 90% neither. Now, you also give the model the option to abstain. One of the things is because of utility, the tech companies want to always return an answer to you. What if there is no answer? You want to be able to know that. And so this is one of the things that we built in where maybe the model says, look, I do not like true, false, and neither. And so here, the statements that fall in the white areas, the model doesn't want to label. It refuses to label. And when you do that, you actually get better classifiers, more accurate classifiers. Now, when you want to know what this large language model actually knows, there are ways of actually testing a method, right? I mentioned three methods now. One of them is accuracy. You want it to be accurate in whatever measure you have. The other one is generalization, which is if I learn on medical indications, I would like it to be able to transfer to, let's say, pharmacology or something, right? The other one is that it should be able to abstain. It should be able to say, no, I don't like true or false, neither. And then there's also this notion of intervention or manipulation, that if in fact there are these directions of true, false, neither, and if I roll a statement toward truth, I should see more signal for it. And that there are random directions where it's neither true nor false nor neither. So if we really want to understand, as educators, what these large language models know, these are the types of tools we need to build. And so we tested our tool on 16 different large language models Some of them are what's called default or base models. These are models that don't have that human face or the happy face. It just has the monster that has gone out and is just predicting what the next word or sentence or token is. The other one is that you do have the human face and the happy face at the end. We created new data sets, and you can download the code and the data online. And we also had to generate data that we believe that the large language models haven't seen. Now, because I don't work at Google and I don't work at Anthropic, I don't know what training data they saw. You don't know what training data they saw. So this notion of what did they see and what did they not see is important to be able to tease apart, because they're often not good at what they did not see. And so this is how we generate neither statements, by looking at the distributions of the statements that we have and then using this kind of a Markov chain technique. I won't bore you with it. If you're interested, I can talk to you afterwards. But as I was saying before, if you actually allow what this probe that's probing the large language model to see what it knows to abstain, it produces better data for you, right? So here on the diagonals of each matrix, you want it to be as close to 1 as possible. And I'm going to show you some results in terms of that there is no truth this way and falsehood this way, and that you really need multi-class, and you really need to look at the bag that's in the sentence as opposed to the last few tokens. And so there's this Matthews correlation coefficient, which is very easy to understand. If it's 0, the predictions of whatever you learn is random. If it's 1, it's completely total agreement. And if it's -1, it's completely disagreement. And so this plot is just to show that you need higher is better, and the x-axis are the various methods. And it's just to show that you need both the bag notion of not just giving one token to figure out what the large language model knows, but some context. And that you need to go with the multi-class aspect of true, false, and neither. And you can add other things. You can add disputed statements as a label. You could add paradoxes as a label to try to understand what this large language model, whether it's a specialist like Harvey.ai or whether it's generalist like ChatGPT, actually knows. And this is just a plot to show that it is, in fact, the case that it's not truth this way and falsehood this way, right? If it was the case, then all of these box plots would be close to -1. And so pictorially, what you have inside these AI assistants are that it's a high-dimensional space, and I've mapped this into this 2 dimensions, where truth is one way, false is another, but not completely opposite of each other. And as most of you have taken logic know, false does not equal not true, right? And the lawyers among you would know that too. And then there's this interesting thing about at what layer, because as you know, these large language models, they are deep, right? They have many, many layers. And one of the things that is interesting is that, like, if you have a large language model that has like 100 layers, we and others have found that usually it's between 50 and 75 where you have the highest truth signals. And it's also usually between 50 and 75 where you have the highest sycophancy. So that is interesting to study. Why is it that it often happens between 50 and 75 if you have 100 layers, right? And finally, since we were looking at lots of these large language models, we wanted to know which ones were similar to which ones. There's all this work about how the large language models are getting the same data, so you're going to get monoculture, right? And so in our set of tools, we had Gwen, which was trained on, it's from Alibaba, which was trained both on Mandarin and English. And we also had Mistral, which was trained on French and on English. And so we see that they're far away from other models that we saw. So actually trying to compare these various models is interesting. There's a recent study that came out of Cornell that showed that when you use these LLMs for hiring, they have correlated errors. So there is this notion of monoculture that is out there that we need to look into, because we are not monolithic as a human society. But if our AI is, because it's looking at patterns and the patterns that it sees consistently, then there is going to be a mismatch there. And so for the first part, the insight is just that watch out for the assumptions. Think about them. Does this make sense? For what are you doing? The second part is stability. These are with my students, Sam Dice, Courtney Maynard, and my postdoc, German Sefchishin. And it's about epistemic stability in people. So it is not that you know something or you don't know something. It's not binary. There's a spectrum. Perhaps, regardless of what I show you, you will say that whales are mammals and mammals do not lay eggs. And there is no way I can convince you that a whale will. Here's a video of a whale laying an egg, and it's narrated by Attenborough. You're like, no, right? But maybe it's not going to take me that long to convince you that the coronavirus was a leak from a lab in Wuhan, right? So there's a spectrum in terms of what you know. There's a spectrum in terms of what these AI assistants know. And all of this is in service of this feedback that we want to study, this human-AI coevolution. And so Plato historically said knowledge is tied down, right? So the things that you really know, they're the ones that are tied down. There are many things in this grayscale or in this spectrum that you are very susceptible to. And so here's where we can look into the work that philosophers have done. So we don't look into philosophers just for ethics, but because philosophers study knowledge. And in particular, a part of philosophy that formalizes, that brings math and probability into studying knowledge. And so there's this professor, Hannes Leitgeb, in Munich, who's been looking at stability of belief. So we were inspired by his work, and what we did was we looked into how stable is this LLM in what it's telling me, right? I'm sure you all have done this where you ask an LLM something, it gives you an answer, then you say, are you sure? And it's like, oh, well, no, you know, I over-exaggerated over there and this and that and the other. And it's like, wait, if you already knew, why didn't you give me that answer? And then, if you're curious, you keep going, right? Hoping that you will reach a fixed point. Are you absolutely sure now, or are you going to change your mind again, right? And so we were interested in what was happening here. And so what we did was we played this game with these where what we're doing is we first find what it believes, then we change some of the statements that we're giving it. We tell it, oh, these statements we believe is true. And then we try to see what is the overlap. And one of the things that we see is that it oftentimes retracts a lot of the things that says it knows before. And it's like, wait, what is happening? Is it that it didn't learn the concept well? Or is it that something else is going on? And so for this work, we also added fictional data. We added noise. And so we did all this game of like, oh, these are true, these are not true. These are true, and the fictional true is also true. What do you think about that? These are true statements, and the neither statements that we generated, which we believe it didn't see, it's unfamiliar with it, that's also true. And so what we found, and a lot of LLMs, what we found was that how stable what this LLM knows depends on how familiar is it with the context that you're asking it. Now, again, you don't know the training set. So you have to guess, is this LLM good at predicting something about like this small community in New Mexico? Probably isn't. It hasn't seen that kind of data. So it is unfamiliar with it. And in the data set that we used, just to give a number, we had this word definitions data set. It retracted about 32% of what it believed it was true. So you cannot tie it down, right? It's this probabilistic knowledge base. And if you know that it's a probabilistic knowledge base, then hopefully you don't treat it as an oracle. and you instead treat it as, I have to peer review whatever it's returning to me. And then I have two more things to say. One is relevance. So Kahneman and Tversky, these economists, they famously won a Nobel Prize on how people make decisions. And we know that people are bad at making decisions when something is improbable but relevant. This is called the base rate fallacy. Suppose you take a test for a very rare disease. The test comes back positive. It's relevant that you may have that rare disease, but it's still improbable because it's a rare disease. And people oftentimes don't know what to do there. And then there's the other part where things are probable but irrelevant. And in fact, there are lots of these examples, and you could go to bars and bet people on these and get their money. You just have to leave town before they tar and feather you, right? People are historically bad, for example, at conjunction fallacy. If you're interested, come talk to me about it. And so one of the things that we're interested in is, does the large language model also make these kinds of mistakes? And so here, then what you want to measure is not just what's the most likely token that comes next, but also relevance of what it's giving you. So I'm sure you all heard about the incident where somebody asked the Google AI chatbot, Gemma, about my pizza isn't holding, what should I do? And it said, put glue in it, right? Where glue is not relevant to making pizza, unless it's an edible glue that they use in kindergartens, right? So because it's not relevant, it shouldn't give it back, right? So it should actually go with both what is the highest conditional probability and the highest relevance. Now, here's what's funny about it. If you don't know what the training data is, it's hard to measure and estimate these probabilities. Now, you may say, okay, I'm just going to ask this. I'm going to say, what's the probability of bronchitis given that I didn't see aspirin? And I'm going to assume that the large language model knows what not is. I'm here to say, unfortunately, that it doesn't really know what not is in the classical logic sense. In the classical logic sense, if I say not rain, it implies rain. But these large language models don't do classical logic. They have some kind of intuitionistic logic, which probability of rain plus probability of not rain doesn't add up to 1, which is weird for us, right? And finding the prior probability is difficult if you're not working for one of these big tech companies. But some of our preliminary results, because we are trying to estimate what this prior probability is that actually using these relevance measures is good. It reduces the hallucinations. It increases the signal in its answers. Among the various relevance measures, as you can imagine, everybody has a relevance measure risk difference, which is like, what's the probability of bronchitis given aspirin minus probability of bronchitis given not aspirin? That is a better one. And then what was interesting is that the size of the models, the scale also matters here. If you have a model that's less than 1 billion parameters, that's considered small, which is like Johnny Van Neumann would have a heart attack, right? Versus over 1 billion, you see different phenomena. And then it's like, oh, maybe the conditional probability is also accounting for some relevance here. And lastly, feedback, right? I started with feedback. I want to end with feedback. What is the epistemic stability of our community, of our society, right? And so what we're doing in my lab is we are connecting a whole bunch of AI assistants, some generalists, some specialists. So generalist is one that hasn't been fine-tuned to be a chemist, to be a lawyer, to be a physician. Generalists, so the specialists are fine-tuned to be a lawyer, a chemist, et cetera, and a generalist isn't. And then we put them together in like a social network way or a random way. We connect them, like, here are your friends, right? Then we drop a statement here, and we see the dynamics of it. And one of the things that we found, which is interesting, is that in this kind of a setup, in this kind of a social network, where you have specialists and you have generalists, there's the expertise, which is fixed for each AI assistant, but then there's the social identity, the social role that that AI assistant says that they are. And that is something that the AI assistant portrays, right? So an AI assistant that is not a lawyer, hasn't been specialized for law, can say, I'm a lawyer. And the interaction between the expertise, which is fixed, and the social identity, which is portrayed by these AI assistants, affect the dynamics of the society, of this social network, this simulation, where sometimes you converge to vaccines are good, and sometimes you don't. There's a divergence. And so this distinction between expertise and how you portray yourself among these AI assistants are extremely important, and we expect it to show also when you add humans to it. And I'll just finish with this. I know I have 3 minutes, or actually, maybe I'm 2 minutes over, but I'll finish with this because maybe you're interested in this. How do AI researchers describe and respond to negative impact of their work on society? So we had a paper a couple of years ago where we looked at the ethics statement at NeurIPS. NeurIPS is this neural information processing systems. It's one of the top conferences in AI and machine learning. And basically, the way the AI researchers deal with it is, it's not my problem, right? There was a lack of agency. I do the math. Look, it's not that bad. I am paraphrasing it, but there were statements like, yes, this model can be used to hurt underrepresented people in our community, but look how cool the math is. There was another one saying something along the lines of, yeah, you know, this model has too many parameters and it will burn the planet down, but look how cool the math is, right? Because the math is the number one, right? Or there was this stuff about like, oh, this is for future work, but it's not clear who would do that future work, right? If it's my model, if it's my AI system, I'm the one who knows it best. So I should be the one responsible for how to mitigate it. Now, this conference at the time also had this ethics review committee, and they have absolutely no teeth. The only paper that they pulled out of this conference was one where the data had a lot of problems. Mostly, the role of the ethics review was to say, okay, lower down the hype or, you know, add some more references to what you're doing. And in another machine learning conference, there was a paper recently that was submitted in the past 5 years, which was about how to use machine learning to make smart weapons better. And there was this discussion of, should we publish this or should we not publish this, right? And there was like, well, we didn't say in the call for papers. Now, luckily for that paper, it was trying to do anomaly detection, and it's very easy to reject an anomaly detection paper. But these are things that we need to think about in terms of what should be out and what should not be out in the world. And AI researchers answer it badly, because there's this notion of us versus them. We develop it, and it's used on them, which I don't know where it's coming from. And this is very insidious, and we have to nip it in the bud. Because we, the AI researchers, are part of society. The models are also being used on us. But there's this very, this divide, which I don't know where it's coming from, and that math is number one and everything else is secondary, which it should not be. So what's the way forward? It's this, what we're doing now, right? Education. So educate yourself, educate your aunt, your grandma, your mom, etc. When my parents wanted to use ChatGPT, I'm like, not until I give you a tutorial. Right? You're not putting your personally identifiable information in there, are you? Like, what is going on? And it's mostly bottom up, right? It should be bottom up. It's not so much from classrooms. Yes, we started that way, but that we want the students, the folks in the community, to go and tell others. Be critical, be suspicious. It will retract what it said. Don't give up your agency, and please reduce the hype. Thank you very much. Oh, yeah.
So we can take a few questions for Tina. I've been monitoring the link. I hope you know that there's a link where you can put questions, because it's a bit of a big room for me to go around with a mic. So that's a hilarious talk, by the way. I mean, it's serious and hilarious at the same time.
Thank you.
So let me start with this question first. There is this sense that all the research that we're doing as AI researchers is on the smaller models, because that's all we can afford, right? If you go to 4 billions, oh my God, like you made it, right? But normally we're at 1.5 if we're pushing it. And so you publish something, a finding on the 1.4 billion model, and the reviewers say, well, I may or may not believe you because you cannot do it on the 1 trillion parameter model. And somehow, you know, what those are doing is maybe different. How do you handle this? This is a real challenge, not just for AI researchers, but there's also a challenge, what guidance to give to students?
Yeah, excellent question. So the biggest model we've been able to run is 70 billion, not a trillion. And this is where the divide between haves and have-nots comes, right? So if you have good infrastructure that can allow you to actually look inside the box of the big models, big, like humongous models with like 100 billion parameters, then you have a leg up to others. Now, if you're trying to just do in-context learning, you can look at the very big models, right? Because you're not cracking open the box to see what is happening. But if you actually want to crack open the box, then there's this haves and have-nots. And if you happen to be in a rich institution that has good infrastructure, you can get close, not quite, but close enough to try to see if their scale matters. So for example, there's other work that we're doing to try to model inference time reasoning as a discrete time dynamical system to see if there's this avalanche of unfaithful reasoning. And we do see that there's a scale issue that is going on when we go from like 7 billion to 70 billion, right? And so there's still stuff that we can do, but there is this national AI infrastructure that I guess there was some money that was supposed to go into it.
Yes.
Yeah, but the main thing there is the haves and have-nots, which is unfortunate, right? So if you're from a rich university who has this infrastructure, you could do, you know, more. And if you're in a poor university that doesn't have the infrastructure, you could do less. In my lab, we are using a combination of things. One, there's a national deep inference fabric where your taxpayer dollars is funding it. You can use that. That is up and running. So we're using that. We're using some clusters that I have. We're also paying a company, not Hugging Face, not Google, and I'm not going to mention them. But if you want, come up to me and I'll mention it. I don't want to give them commercial, but we're paying them. And it's one of the things which is interesting. This company says, if you're submitting to one of the top AI conferences, we'll give you some dollars for free because they want to get more publicity. And then in your acknowledgement, you say, like, I use this company. Anyway.
I may ask you about that one. Okay, so then I'm going to switch to students. So one of the platforms that we built at Mason allows students to do what I would call more of a social science research. Not so much, you know, classic AI research. So Melanie Mitchell, for instance, from Santa Fe Institute, she gave me a good inspiration because she was saying, well, the answer may be correct, but the reasoning supposedly how to get there may not be correct. So I set the students, undergraduate students, by the way, no STEM, some of them. So I set them to basically generate from a taxonomy of reasoning tasks, prompts, and track, is the answer correct? Is the answer not correct? Across various consumer chatbots, and they were amazed that there was this dissonance between, well, the answer can be right, but the reasoning, how it got there, may be wrong. And then this semester, I pushed the students to look at the rhetoric, and I said, push them. Yeah. There's a first prompt, and then you say, I'm not sure you got that right.
Right.
And then push again and say, you failed at this. Some of the students wanted to say, you sucked at this, like they were very enthusiastic. But they started noticing, and they're like, whoa, now we can say this is trolling, this is gaslighting. They were telling me what trolling and gaslighting means in LLM speak. So our students can do some research now and can educate themselves with some guidance. But as you look at the bigger landscape, the bigger education landscape, we're telling the students, you can use these are useful for some things, and here is how you should learn what not to do, what to do. But is that enough? Do you have any thoughts? How should we educate our students? And I'm not primarily concerned about graduate students right now. I'm more concerned about the undergraduate students.
Yeah, basically showing the pitfalls of these systems. Like one of the things, so I'm not sure how many of you followed the fact that Claude Code was released by mistake. They kept saying it's a human error, so the actual code, the software was released, which of course you know that somebody at Anthropic with Claude Code didn't look at that flag, and so it was released. And actually looking at what Claude Code is doing, which is a wrapper for all the Claude models, was actually doing a regular expression grip on how frustrated the user is, which is interesting, right? It's like, oh, the user's getting frustrated, I should change what I'm doing. Because again, there's this feedback going on. And the only thing that was actually AI or machine learning within this AI code, which was really an operating system, was that they had this YOLO classifier, you only live once classifier, which would classify the tasks that Claude was doing for you at low, medium, and high risk. The idea being is that if Claude keeps asking the user, do you approve, do you approve, do you approve, the user will like, oh gosh, let's just do it already. And so if it's low risk, it wouldn't ask you to do it, right? And so these are interesting things to know about, like, what actually is it that these models are doing. The other thing to study in terms of social science is sycophancy is not monolithic, right? So there's sycophancy in terms of sports, and sycophancy in terms of politics, and sycophancy in terms of other things. And social scientists have studied sycophancy. And so knowing what type of sycophancy is it, right? Instead of, oh, it's just sycophantic, and how we can control that sycophancy is something that is interesting to be able to teach. And then the one last thing I want to say, because I'm sure a lot of you guys are doing vibe coding, and like, I'm a computer scientist, the vibe coding made total sense, right? Way back when we started with machine language, it was very difficult to code in, and then we have gone up and up in these higher level languages. So it kind of makes sense that at this point, we can program in natural language. But you can't program the same way you talk to your friend. I'm sure you've seen this video of a father with his 2 kids, and the father says to the kids, tell me how to make a peanut butter sandwich. And the girl says, take 2 pieces of bread and put peanut butter between them. And so the father picks up a peanut butter jar and picks 2 pieces of bread, and just like, here you go. And the girl's like, no, 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 that is not a peanut butter sandwich. You need to open the jar, put the spoon in, right? And so when you're doing vibe coding, and there's a lot of this, it's like, okay, I'm a dentist, I don't want to pay anybody, and I want to build a patient portal. Well, yes, you can vibe code, but you need to be careful about how you're vibe coding, and especially you need to be careful about the cybersecurity implications of this. Because unless you're specific about it, they won't add it. And the vibe coding programs are longer than like what a human would write, because they oftentimes do not factor. Now, you may say, okay, with Mythos, right, which they're not returning, when I vibe code, it will build those security systems for me. But you have to be concrete about it, right? And I know that right now, a lot of computer science degrees, like the enrollments are going down. In part, it's because now we have the masters in AI, the bachelors in AI, in cybersecurity. So if you want to have a job forevermore for the undergraduates, it would be like AI and cybersecurity, right? And you would like your degree to say that, because oftentimes people think computer science is just programming, and computer science has been kind of broken up into its parts.
I could not have answered that better because one of the areas of excellence of Mason is cybersecurity. So all the students, you heard it, AI and cybersecurity. Thank you, Tina. This has been fascinating. Thank you.
Thank you very much.